Right now, over the warm heart of the Pacific, a storm is spinning up that has meteorologists watching with quiet alarm. Satellites show a swirl tighter and deeper than any model predicted, sitting over an ocean running hotter than any record in history. Imagine a rain wall taller than the tallest mountains and an eye wider than entire countries. This isn't just weather, it's a heat engine finding a richer fuel supply than ever before. Today, we're diving into the Pacific Engine, the reason why this ocean produces the largest, fastest, and deepest storms on Earth. The science of the heat engine. A tropical storm is essentially a heat engine. It feeds on one thing: heat. When sea surface temperatures hit around 86 degrees Fahrenheit, the lower atmosphere becomes loaded with moisture. As this moisture rises and condenses, it releases the energy that powers the wind. In the Pacific, the atmosphere often creates a clear vertical chimney. Without strong upper-level winds to tear the storm apart, it can grow into a massive vertical pillar stretching from the ocean to the edge of the stratosphere. This leads to a terrifying phenomenon called rapid intensification. This means a storm gains at least 35 miles per hour in wind speed in just 24 hours. We've seen Hurricane Hunter aircraft record pressure drops of 14 millibars in just 6 hours, a rate that places these systems among the fastest deepening cyclones in a decade. The Pacific Advantage: scale and depth. Why is the Pacific so much more dangerous than the Atlantic? First, it's about scale. The Pacific covers 60 million square miles, larger than every continent on Earth combined. A storm here has thousands of miles of uninterrupted warm water to travel across, drifting for weeks and strengthening in stages. Second, it's about depth. While satellites measure the surface, the real story is 50 to 300 feet below. In the western Pacific, warm pool, water above 82 degrees Fahrenheit, extends down for hundreds of feet. In other oceans, a storm's own winds churn up cold water from the depths, effectively poisoning its own fuel supply. But in the Pacific warm pool, the churned-up water is still warm. The fuel never cuts off. The records: Tip versus Patricia. To understand the upper limits of physics, we look at two monsters. First, Super Typhoon Tip in 1979. It was so large its circulation covered 1,380 miles, wider than the distance from New York City to Denver. It remains the largest tropical cyclone ever recorded, with the lowest sea level pressure in history, 870 millibars. Then there is Hurricane Patricia in 2015. While Tip had size, Patricia had the blade. It featured a pinhole eye, less than 10 miles wide. By compressing its core, Patricia's winds exploded from 85 miles per hour to a staggering 215 miles per hour in a single day. It was a spinning buzzsaw that forced scientists to rethink the upper limits of hurricane strength. The human cost and the future. These storms aren't just statistics. The Philippines absorbs roughly 20 storms a year, and the geography there acts like a funnel. During Super Typhoon Haiyan, the shape of the bay forced a storm surge 20 feet high, sweeping ships inland into residential neighborhoods. Even prepared nations like Japan are being tested. Tokyo has built massive underground flood channels to move tens of thousands of cubic meters of water per minute. But as marine heat waves become more frequent, the physical ceiling on how strong a storm can become continues to rise. Adaptation costs are now measured in trillions of dollars. Coastal defenses and early warning systems save lives. But the underlying driver, the heat content of our oceans, is still rising. The storms forming over the Pacific are signals from a system in transition. Each one carries information about what the ocean is absorbing and what the coming decades may hold. The question is, what do we do once we hear the signal? If you found this breakdown helpful, hit the like button and subscribe for more deep dives into the forces shaping our planet. Stay safe.